Okay. So today we will discuss about type 1 factors. For that we will discuss, it's defined based on the properties of the projection. As you know, Von-Neumann algebras are generated by projection. So it's based on the properties of the projection. What kind of projection exists in a Von-Neumann algebra, in the factor. So we are discussing factor. In case I forget to mention, we are discussing factors. Our M will denote a factor. Okay. So before that, maybe I will prove something about the projection. So let M, this is for any Von-Neumann algebra. X is any Von-Neumann algebra. Say it again. I'm going to define. Yeah, I haven't defined. No. Yeah. So X is in M. Then we define L of X. See, if we have a function, this is like if you have a function, then you have a support for that, even for an L infinity function, even for a measure, you have some support for a measure or something. Here it's for a projection. This will be a projection. So if you have a X in M, then L of X is a projection. Onto range of X. Range of X, of course, it may not be X. M is contained in B of X, of course. It may not be closed, so you take the closure. Similarly, R of X, this is called left support. This is for any operator. You don't need to be in M. I say M because I will show that L of X, R of X are in M. Okay. So left support of X. It's for any operator you can define. Similarly, R of X is the projection onto. So there is another, I said, kernel perp of X. Okay. So, of course, if it is self-adjoint, they both coincide. So if it is self-adjoint, right support and left support coincide. And in case for any other operator, if left support and right support coincide, then we call it support. So then the remark is maybe proposition. L of X is the smallest projection such that smallest projection P, in B of X, such that Px equal to X. That's why it's called left support. Similarly, R of X is the smallest projection such that XP, R of X is X, P equal to maybe XQ equal to X. Left support and right support. R of X is the smallest projection. So this is easy to see. Just a remark, but let's just prove it. Why is it true? First, clearly L of X satisfies, the proof is similar for R of X. I prove for L of X. Clearly L of X times X is, because that's on the range, so this is equal to X. That is clear. And you have to show that it is the smallest projection. For that, suppose Px equal to X. Okay. Then it's clear that Px equal to X, then, P acting on the, then you want to show that if Xi is in Xi is in range of X, then that means this is equal to Xi equal to X eta for some eta. Then P acting on X eta equal to X eta equal to Xi. Okay. P is equal to Xi. So this implies P contains, P is identity on range of this. So P contains, range of P. If I write, that will be a problem. Range of P contains range of range of the x. Okay. Similarly, if xq equal to x, then kernel of q is contained in kernel of x. So kernel perf of x is contained in kernel perf of q. Okay, so the statement follows. So if you, so the projection, so kernel perf of q. Kernel perf of q is the range of the projection q. So range of projection q is contained in this. Range of the projection q contains this space. So this implies R of x is smaller than or this for projection, the smaller than or equal. We have a partial order and positive operators. Projections are positive operators. So this less than or equal to that partial order that is same as the range is contained. P1 is contained in PQ. The range of P1 is contained in range of P2 is equal to P1 is smaller than or equal to P2 as positive operators also. So R of x is smaller than or equal to Q. Okay. So all these things are same. So next proposition is x is in the Von-Neumann algebra M, then L of x, R of x, R in M. Proof. So what do you have to show? We have to show that L of x is in M. So to show L of x is in M, we have to show that L of x commutes with L of x is in the double commutant. So L of x commutes with M commutant. That's what you have to show. And any Von Neumann algebra is generated by unitary. So it's enough to show L of x commutes with unitaries in M. Then it will commute with everything in M. Okay. So for U prime in M prime, you want to show that L of x commutes with this. You want to prove U prime L of x, U equal to L of x. That's what you want to show. But notice that this is a projection. This is a projection. Sorry, Ux U prime star. Sorry. That's what commuting means, right? That's what commuting means. So it's star. So notice that this is a projection. If you take this square, this is equal to this, and this is alpha. So this is a projection. So now U prime L of x, U prime star, this projection with x equal to, but this commutes with this x. So you can take it out. Okay? That is U prime L of x as x times U prime star. But this is equal to x by the property of this. So U prime x U prime star, this is equal to x. So U prime L of x U star with x is equal to x. But L of x is the smallest projection satisfying this. Okay, so this implies U prime L of x U prime star is greater than or equal to L of x. Okay, that is the property of the left support. The same proof will work for right support also. But we want equality. This is for all U prime in M prime. But then this map, this map, any map, x going to, if you have a unitary Ux U star, is order preserving. Okay. So it preserves the positivity, the positivity, and it preserves the order. So this implies that this is true for all U prime. So you can apply U prime star on both sides. This will imply Lx is U prime if you apply U prime star, U prime star, U prime. Okay, if you apply this is greater than or equal to U prime star L of x, U prime star, U prime for all U prime in M prime. So this implies L of x is greater than or equal to U prime star L of x for all u prime. So this implies L of x equal to u prime star L of x u prime for all u prime in M prime. Okay. That means it commutes. So this implies L of x is in L of x commutes with all unitaries in M prime, so it commutes with M prime. So L of x is in M. Similarly, the same proof, just flip the sides. Similarly, R of x is also. So these projections are like sets for the non-commutative setup. I mean, in L infinity, the projections are precisely those indicator functions corresponding to set. So here, the projections are like sets. I mean, in the quantum setup or non-commutative setup, projection forms the analog of sets. So we want to do this usual operation, whatever logically AND operation or OR operation or whatever. The sets you take the union is like OR, taking the intersection is like AND. So similarly, such operations we want to take. So further, we define the following. If PQ are projections in M or Vfx, doesn't matter. So, but then P and Q, which is just the intersection, which is just the projection onto P H intersection QH, which is well defined, of course. So I define P, this is equal to, I mean, 1 minus P is the projection onto orthogonal complement. So let's define P prime equal to 1 minus P, or I can write it as 1 minus P. P prime, Q prime, I mean, Q per, P per, Q per. Size. Oh. Let's think about it. But we want to take this projection. This is projection generated by P and Q. If you see, this will contain the projection, range of projection P, range of projection Q, and it is the smallest projection on the space generated by range of P and range of Q. That's how that will be clear from this. If you just look at this definition, it will be clear. I mean, this is P is orthogonal. The range of P is orthogonal to this. Range of Q is also orthogonal to this, and that's the smallest projection. So you can verify with this. Okay, you can verify with Zeiss here. That's a smaller. If you take the space generated by both P and range of P and range of Q, it is just the projection onto the space generated by that span closure of that. But we want to take this P projection generated by infinitely many projections, maybe uncountably many projections. For that, we need to define through strong convergence. Of course, projections are usually, the limit is defined by strong convergence. We can't use norm convergence or any other convergence. So for that, we want the following lemma. So you have a net. We want to use net because we may take infinitely many, I mean, net of projections are infinitely many projections. So lambda, yes. I hope you know a net, what a net is a net of positive operators. Sorry, increasing net. and this is suppose contained in M, a von Neumann algebra. And that is what it means by increasing net is x lambda 1 is less than or equal to x lambda 2 if there is, I mean, this is a partially ordered set. Of course, net is indexed by partially ordered, a partially ordered set if lambda 1 is less than or equal to. Okay. If this partial order is preserved for this, and if it is uniformly bounded and supremum is then there exists here x in M such that x lambda converges to x strongly. Okay. That's all. So you have a uniformly bounded increasing net of positive operators, then there exists a limit. I mean, you only need the increasing one. So this is positive numbers. This is greater than increases, and it is less than or equal to the supremum, supremum of lambda, norm of x lambda times norm z square. It's a increasing net, increasing numbers. These are numbers, positive numbers, and it's bounded. So there exists a limit for this. Okay? For each z, there exists a limit. By polarization identity, you have a limit for each x lambda xi eta as a limit. Or you can define an operator using it. Okay, that's what I want to do. Okay. So define it. X xi eta equal to limit of x lambda xi eta. Okay. L lambda is in. I mean, use polarization identity. Okay. Too long to write. Okay. By polarization identity. Okay. Now this is bounded because x lambda, I mean, this is bounded by supremum of that norm xi, norm eta. Okay. Because of this, because it's defined through the limit. So x is bounded, clearly x is bounded. That's clear, no? Because this is defined as the limit of this. So x is bounded. Okay, so x is bounded. We only have to show that x is the strong limit of that. So we have x lambda minus x xi. So this is right, x minus x lambda. Okay, this is positive and it goes to 0. Okay. Right, this is positive and go to 0. So this implies x minus x lambda power half xi x minus x lambda is power half xi goes to 0. That means x minus x lambda power half xi goes to 0. That is x minus x lambda power half goes to 0 strongly. But then if we have a uniformly bounded net, then strong convergence is continuous in both the variables. I mean, if S lambda converges to S strongly, T lambda converges to T strongly. Of course, for sequences, it will work because that will be uniformly bounded. And the norm of S lambda, norm of T lambda, everything is less than or equal to M. Uniformly bounded. Then you can verify that the product S lambda T lambda will converge to ST. I mean, of course, other way also. This is through triangle inequality and use this bound. I mean, usual. I mean, you will take out the norm inequality, triangle inequality, and all that will follow. So it's an exercise. I think I mentioned it before. On uniformly, I mean, generally on one side, I mean, if S lambda converges to S, then S lambda T will converges to ST. And T lambda S converges to TS. Okay, on one side, I mean, whatever. I mean, it's continuous in one variable, And both the variable it is continuous. This multiplication is continuous in both the variables if it's uniformly bounded, which you can verify by using this inequality. Okay, with an exercise. So because of that, x minus x lambda will converge just to 0 strongly. Okay, that's what we want. I mean, it just apply x minus x lambda. So it's just the square. Okay? So this will converge to 0. Okay. Now using this, we can define further projections. So let P lambda maybe Pi, I in I. I is any indexing set, okay? Any indexing set is a family of projections. And this is not a net or something. This is not the net, family of projections. Then you define a finite set contained in a finite set. Define P that finite set, or I'll just set it smaller. For any finite set contained in the indexing set, you can define, I mean, projection defined by Pi1, Pi2, Pi if f is equal to I1 up to In. Okay. This you can define. Finite for finitely many, you can just define. This is the projection onto the space generated by all these finite projections. But then we know that, so this PF, now you have let F be all finite sets, all finite subsets of I. This is a totally ordered. This is a this is a partially ordered set, right? With inclusion. Okay. Set with inclusion, of course. Then this is an increasing net. This is an increasing net indexed by all finite set, PF, F containing infinite set, collection of finite set. This is an increasing. This has a limit, has a strong limit. Strong limit by the previous proposition. And we call that as strong limit, let us say P. Then that P, we call that as I in I, PF. When union, I mean the V operation, whatever, it's not union, it's a V operation of all this Pi or OR operation in quantum logic is just this. Okay. Okay, so I want to have prove two more lemma before defining what is type 1. So this is the lemma. Of course, this is a strong limit. So this is in the phenomenal algebra. PIs are in the phenomenal algebra. Then this P, the projection generated by all these PIs also in phenomenal algebra. Let P, now I assume it's a factor. Suppose you have two projections. Huh? The center is trivial. Okay, so Z of M is M intersection M prime is C as the one. So if you have two elements in a factor, then there exists a unitary U in M such that P, U, Q is not equal to 0. we want to exhibit a partial isometry such that UU star comes under P and UU star U comes under Q. I mean, P, Q are some projection, so we have a range something, we have something. Then we want to have a partial isometry between them. It may not be exactly equal to that, but it will go to a subspace of this. That's what we want to do in the next lemma. For that, we use this lemma. Okay. If we have two projection, then there exists a unitary such that PUQ is not equal to 0. So we just have to produce one. So suppose PUQ equals 0 for all U in M unitary. So then, of course, U star PU, we just apply this Q, is also equal to 0. Okay. Now this is a projection, right? U star PU is a projection, right? Now you take this projection. Of course, if you have 0 projection, then if you have all this net, it will give rise to 0 only. Because if you take finitely many of them, it is 0, and the limit is also 0. So U in U of M is the unitary, okay? Unitary is in M. This is my notation. I don't know whether I used this. U of M is the unitaries in M. So you take the all unitaries in M and then use this projection here. This is the single projection. Okay. That acting on Q is 0. Okay. Here it's supposed to be P and Q are not equal to 0, of course. But 0 projection, such thing is not true. P and Q are not equal to 0. Okay. So now notice that you call this as some U, big U. Now notice, so now this U in U of M, unitary is in M, U star PU is in M, of course. And it is also in M prime. Since for U prime in M prime, no, it's also in M prime, sorry. If you have any, if you have a U prime in M prime, then U prime, each of this. What do you want to say? I want to show that it is in M prime. This commutes with anything in M. Sorry. No, not U prime in M. Since if you have any single U in M, I mean, let's B in M, you have any unitary in M, okay, then B star U star PU B, you just take it, or this, you take this. Okay. This, when you index it by U in M, is actually equal to V this. You just verify this. U in M. I mean, this V is this is small v. Okay. This is small v, which is unitary. That is big V, which is operation V. Okay. U star PU V star. Okay. I mean, this is equal to this, but then this will index over all of them. This is equal to precisely equal to this U in M. I mean, unitary forms a group. If you multiply, hit it everything by a M, it'll just it's a translation. I mean, it's just the it just shifts and it's an automorphism. So U star PU only. Okay. So this is equal to this. This is equal to this. So because of that, this commutes. Okay. This because of that, this commutes. Is in M prime. So that is in M and M prime. So it's a scalar, and it's a unitary. So it has to be identity. It has to be identity, and it's positive and all that. I mean, it's a projection. So it's a positive projection which is in M and M prime. So it's identity. This implies this U in M, UP U star equal to identity. This is the projection. Okay, this is the projection, and that is both in M and M prime because M is a factor. Okay, since M is a factor, so this is true only in a factor. Okay. This is the identity, but then identity times Q equal to 0 will imply Q equal to 0. So this implies Q is equal to 0, which is a contradiction. So there exists a unitary such that PUQ not equal to 0. Okay. So if PUQ equal to 0, then we take this unitary, multiply that, unitary, and get this family of projection, take the projection generated by that, that is actually identity. That's it. So there exists a unitary. Now another lemma or proposition. This can be called as a proposition. So PQ are projections in M, projections, and P not equal to 0, not equal to Q. Then there exists a partial isometry. U in M such that U star U is less than or equal. U star U is a projection. That's what partial isometry means. And U star is a projection which is less than or equal to Q. Okay. So there exists a subspace of range of P, a subspace of range of Q, which are intertwined by actually unitary between them. Okay. Partial isometry is restricted unitary. If you just restrict to the initial space and final space, the initial space is contained in B, final space is contained in Q, and this U is a unitary between them. Okay. Yeah, U non-zero, yeah. Yeah. True. So choose unitary or even X is enough, X in M, such that PXQ is not equal to 0. Okay. And here I want to use and PXQ equal to U mod PXQ with a polar decomposition. It will be the polar, and this U will do, and then U is in M, of course. Okay. We want to show that this U satisfies that property, and that is just clear. We know because it's polar decomposition, kernel of U equal to kernel of PXQ because it's polar decomposition. Okay. So that means kernel perp of PXQ is equal to kernel perp of PX, kernel perp of there is a list. Kernel perp of no, kernel this, wait a minute. Kernel U is contained in this, and so this contains kernel of Q, of course. Okay. So kernel of, this contains kernel of Q. If Q of something is 0, then this is 0. So kernel perp of this implies kernel perp of U is contained in kernel perp of Q. Okay. This is the initial space of U, of course. Kernel perp of U is the initial space of U if you have a partial isometry. If you have a partial isometry, the initial space is kernel perp, final space is range of U. Okay. So this is U star U, and that is U star. So similarly, and also range of PXQ is contained in range of P. Range of P and range of P. And what do we have? We have and this contains range of range of range of let's range of P, and this contains range of U, right? Which is kernel perp of U star, right? This is equal to kernel perp of range of P, which is equal to kernel perp of QXP, QX star P, whatever. Okay. And this contains kernel perp of, here you got P here. So this contains kernel perp of U star, which is the range of that, no? Which is equal to range of U. Range of U is closed. So range of U. So this implies U star U. That implies U star U is less than or equal to P, and U star is less than or equal to U star less than or equal to Q. I have interchanged Q and P. Doesn't matter. U star is less than or equal to P. I had written U star U is less than or equal to P, but I have interchanged it. Okay. Doesn't matter. Okay. So it follows. Okay. So given two projection, we can find a partial isometry such that the initial space of the partial isometry is contained in range of P, and final space of the partial isometry is contained in Q. So now we define what is called a minimal projection. The minimal projection if this is also a projection. Yes. 0 not equal to Q, less than or equal to P for some projection Q in projection in M. By this I mean projections in M. Then Q equal to P. There is no non-trivial projection contained in P. This is the non-commutative analog of what is called atom in a measure space. Atom in a measure space is you have a set B, which is of course in the sigma algebra. And if you have a contained in B, such that mu of A is positive, it's not a zero set means, a set is, indicator function should not be zero. So if mu of A is strictly positive, then mu of A should be equal to mu of P. Okay? So that's what is called atom in a measure space. This is the analog of atom. Atom is a set where you don't have a non-trivial set having a positive measure. Non-trivial set smaller than having a positive measure smaller than that. Okay. So this is the definition. So from this, we want to have immediate, not corollary, as a remark, immediate observation. The first observation is PMP. This is a Van Neumann algebra, we know. If you have a PMP, P is minimal. And PM is a factor. Okay. Then PMB is isomorphic to C. That is clear. If there exists, if this is not C, it's some non-trivial Van Neumann algebra, then there will exist a projection. P is the identity in this, less than that. Okay. And that will be less than this, which is not possible. So it's clearly PMP is C, right? P is the minimal projection, means P cannot contain a projection less than this. If Q is the projection less than this, I mean, if it has a non-trivial projection, suppose Q in PMP is a projection, then Q is equal to some PM, then Q is equal to PQP, right? Okay, this will look like this. So this is a projection contained in P, which then it has to be equal to P. So that's all. So this is just C times P. C times P if you want. PMPs are isomorphic to C times P. Equal to C times P. Second thing is, if PQ in M are minimal, or two minimal projections, no, let's not do that. Of course, if it's a factor, there will exist something. Let me say this. If U in M such that U star U is minimal, then U star is also minimal. So if you have a partial isometry whose initial space is minimal, then the final space is also minimal. That is clear. So if U star contains some Q not equal to 0, okay, then U star QU, okay, this is a projection contained in P. Because this U is a, I mean, P and Q is suppose, I mean, U star U is a projection, I mean, where this is contained in U star U. There is no P, there's only Q. I'm saying that if U is a partial isometry such that U star U is minimal, then I want to prove U star is also minimal. Suppose you have a Q not equal to 0, less than U star, then you use U star QU, which is less than or equal to U star U, of course. Okay, I mean, that's clear. Okay, and if you want U star, so, but this is minimal, so U star QU equal to U star U itself. Now you apply U star U star, okay, this is equal to U star U. This is equal to Q. Now if you apply here, that will be U star. U star U, yeah, U star. If you apply U star here, I mean, it will get, if you apply U and U here, you will get, this is the projection, so you will U star U. And if I apply this, see, U star, U is a unitary between P and Q. I mean, U is a, you have, this is U star U, this space, okay? You have something like this. This is kernel, and this is U star U. And this is the range U star. And from here to here, it is 0. I mean, U maps from here to here 0. U from here to here is unitary, and U star from here to here is unitary. Okay, and here it is 0. U star is 0. Okay, now U star, if you just have something, it will be just Q. This is U star is identity here, identity on this. Okay, U star is identity on this. So U star Q, U star is just Q. You can sit and verify use the property of partial isometry, and it will be clear. Okay, so this is equal to Q, so that is equal to that U star U. Okay, I mean, which is equal to, yeah, which is equal to U star, right? Which is equal to U star. I'm sorry. I mean, if you apply U and U star here, then it's just U star. Sorry. Let me write. I have U star U, Q U is U star Q U is less than or equal to U star U. Okay, but since this is a minimal projection, this should be equal. Apply U star here, and apply U star. I mean, U star U. This is, yeah. if you apply UU star here, you will get UU star here, right? Which is equal to UU star, which is equal to, this is equal to Q. Okay? I'm just saying this is equal to Q. So Q equal to UU star. Okay? So this implies UU is also minimal. So if U star U is minimal, UU star is also minimal. So in particular, third observation, M is a factor and PQ minimal projection. Then there exists a partial isometry. Because M is a factor, there will exist a partial isometry which will take something under P and the range space will be under Q by that lemma. So there exists a partial isometry U in M such that U star U equal to P, but then there is nothing less than P. So it should be equal to that. Okay. And UU star equal to Q. There we have, by that lemma, something is less than P, but this is not zero. So it should be equal to this and it should be equal to that. So if you have two minimal projection, they are intertwined by a partial isometry, okay, in a factor. So definition, a factor M contained in B of H is said to be type 1 if it contains minimal projection. There exists minimal projection. That is, the measure space is, it's atomic. Okay. We'll show that it's completely atomic. You'll show that minimal projection actually will generate. If it exists, if the minimal projection exists, using the fact that it is a factor, you'll show that it is actually generated by minimal projections. Examples. MLC, for example, or B of H. These are examples. You take one-dimensional projections. That's a minimal projection. There is no other minimal projection. Minimal projections are one-dimensional projections. Okay. So if you have a one-dimensional projection, then there is nothing less than that. Okay. So one-dimensional projection. They are the minimal projections in B of H and MLC. And you can take another example is you take B of H tensor 1 contained in B of H tensor K. Okay. Here you take any one-dimensional projection, tensor 1, okay, is minimal. And they are, of course, they are the only minimal projections. But then these are infinite dimensional. You take a one-dimensional projection, but you are tensoring with 1. So it will be an infinite dimensional projection. It will be the dimension of K will be there. Okay. So we want to show that every type 1 will look like this, B of H tensor 1. That's the classification. So we have all type 1 factors. There are only countably many in this universe. Okay. So this is the proposition. Let M is contained in B of H, a type 1 factor, that is, it contains minimal projection. Okay. Then there exists a H naught K. We always assume separable Hilbert spaces, so no need to confuse Hilbert spaces such that and a U and a unitary U give you from H naught tensor K to H such that U 1 tensor P of H U star. Okay, this is a very nice isomorphism is M. M looks like this. For the statement. M is a type 1 factor. Then H can be written as, I mean, that's what it, if you have a unitary means it can be written like that. H can be written as some H0 tensor K, that's a unitary, and this M will look like 1 tensor B of H. So this is a very clear statement. We have a unitary, the identification is through the unitary. So we have to produce a H0, we have to produce K, we have to produce the unitary so that this condition is satisfied. So we have one minimal projection, P. So there will exist, so let, and we don't know how many exist, but let's assume that let P1, P2, P3 be a collection of contained in M, be a collection of minimal projections. We will use, of course, Zone's lemma. I mean, let's not use Zone's lemma and other thing. You have a collection of minimal projection such that Pi is orthogonal to Pj. What I mean is the range of Pi is orthogonal to Pi is orthogonal to range of Pj. This is a collection of for all I not equal to 0. I mean, this is a collection of mutually orthogonal projections which are minimal. Okay, and we of course you can, if this argument is repeated, you can take such collection, and this will satisfy axioms of Zone's lemma, and you will get a maximal. Okay, be a maximal collection. Use Zone's lemma. You have a maximal collection from this. And it will be, of course, countable because the space is separable. This is mutually orthogonal. Okay, you will have at most countable. You can have one vector from that. That will form a collection of orthogonal vectors, and it can be countable only because H is separable. So this will be a countable collection. Okay, so you have a maximal countable collection of minimal projection. The claim is summation Pn equal to 1. 1 is the identity in strong topology. Okay. So if not, then of course 1 minus summation Pn is a projection. I mean, summation Pn is the projection. I mean, if you have orthogonal projection, the sum is the projection generated by those two projections. Right? If P1 is orthogonal to P2, P1 plus P2 is the projection onto the projection and the space generated by P1 and P2. So 1 minus Pn is orthogonal to all Pn for all n. Okay. Now this is a projection, you call it P or something. Now by lemma, there exists a partial isometry such that U star U equal to P1 and U star is less than or equal to 1 minus summation Pn. I mean, any two projection you can get it, but it will come under this. But then if U star U is a minimal, then U star is minimal. So you have a minimal something which is in the orthogonal complement of all these projections. So which contradicts the maximality. Okay, so this contradicts maximality. So summation Pn equal to 1. So it should be identity. So you have minimal projection, collection of minimal projection which are mutually orthogonal to each other and whose sum up to 1. The sum is in the strong topology. So, okay. So these are all factors. So there exists un in M partial isometry such that un star un equal to P1, you take P1, and un star equal to Pn by lemma. Because it's minimal, it has to be equal. I mean, by the lemma, you have partial isometry such that this is less than or equal to P1, this is less than or equal to Pn. But because it's minimal, they have to be equal. Okay, this is equal to this. Un star un equal to P1, un star equal to un star un equal to P1, this is equal to Pn. Okay. Then let X be in M. Now it's clear. Then X is equal to summation Pn X. This is the identity, right? Summation Pn. Okay. A strong convergence, you can write it like this. Okay. And these are all different variables, N and M. So the sum is in the strong convergence. Okay. The strong topology, N and M, Pn X Pn. Okay. The strong topology, you can write it like this. Any X, you can write it like this. Okay. I mean, I'm just applying identity and identity here, which are identity. So now I want to show that this is scalar times P1. Why is this true? Now Pn X Pm equal to Pn is un star. un star X u m star. You can see that this is in, okay. I'm considering this Pn X Pm equal to un star X um star. Okay. By definition. So now apply, note Pn un star, I take this. Okay. X Pn. Okay. What is Pn? Un star un star X star Okay. Now un star acting on un star is identity. Okay. Right? Or un star. Wait. I want to get un star again. Yeah. No. Un star. You have un star. Un star is the final space of un. Un star acting on un star is just un star. Similarly for here. Okay. This is equal to un star X Okay. So Pn of this is same as this. And if you remember, if you have I don't know whether I mentioned it, this is just a remark. If you have a von Neumann algebra, X is in von Neumann, P is in von Neumann algebra, a projection, then we have this PMP, which is actually all those PXP X in M. That's clear. I mean, sorry, all this, sorry, I mean, that is how it's defined. What I mean is all those x in M such that x equal to PHP. Or I don't even need that. I don't even, that's true, but I don't need that. Sorry, I don't need it. This directly implies that, no? I mean, I have that. This implies this whatever this, you call it y. Okay, Pn y Pn. Not Pn. P1, sorry, P1. This is P1. UN star UN is P1, right? UN star UN is P1. P1. Okay. So P1 star P1. So we have P1 y P1 equal to y. This implies y is in P1 M P1. Okay, that's what I'm saying. This is clear. Okay. But then this is minimal projection, so this is C times P1. Because P1 is a minimal projection, we noticed if you hit a Feynman algebra with minimal projection, you get constant times P1. We have noticed, it was a remark. So this implies whatever we have here, Pn x Pm equal to some lambda times Nm, which depends on that, times Um star. That's all. This star act on the range of P1. Where does U1 go? Sorry, times P1. Sorry. Yeah, times. Where does P1 go? P1 will be in the middle, right? U1, P1, UN, P1, UM star. Okay. What it does is the following. I mean, this is just notation. What it does is the following. You have, see, if you have H, which is equal to direct sum of range of Pn, right? H is direct sum of because summation Pn equal to 1. So H is range of P. So how our operator X acts on this? Our operator is in M, which is a type 1 factor. How it acts is, it takes something in the range of N, brings it to, if you apply UM star, sorry, if there is range of M, for example, how it acts on the range of M. It will take something in range of M to bring it to range of 1, P1, and apply this P1 on, I mean, so apply P1. P1 is just whatever. I mean, P1 is just identity on that. So that is why P1 is not there. P1 is not, P1 will go away when you have UM star. P1 will go away, sorry. It is just UM star. P1 times UM or this is, that will absorb there. So, okay, so there is no P1. Okay, so this is just UM star. So it takes anything in the range P1, it applies this partial isometry and brings it to P1. Then UN it acts on that, it will go to Pn, Pn. Okay, so it is just basically this lambda determines this. So our X is just a matrix on this. Make it precise. So let H0 equal to P1H. Okay, and K equal to L2N. Okay, and define U from, which is defined on the total set. It's enough to define on total set and verify it preserves the inner product. So which is H0 tensor L2N to H by U acting on any xi naught tensor F equal to summation F of n U n xi naught. Okay. Because this is an orthogonal sum, this is in L2, this makes sense, of course. F of n is in L2, so this makes sense. And this is a vector in the range of Pn. Xi naught is a vector. I am having H0 equal to P1H. Xi naught is a vector here. I am taking tensor product H0 tensor L2n. I take an elementary tensor, I define like this. I take a xi naught tensor F. F is a function, L2 function. or a sequence, whatever. So it takes this to f of n at the nth place and un xi naught. This is in the nth Hilbert space. Okay. So now you can verify that this preserves the inner product. Which is clear. U of xi naught tensor f, U of eta naught tensor from G, the inner product, which is equal to the inner product of summation over n, f of n, un xi naught, g of n, un eta naught. And of course, you know that for n not equal to maybe m. N not equal to m, they are orthogonal. So this is the summation over n, f of n. Is inner product, you take it as g of m bar. Then it is just, but then this is un of xi naught, um of xi eta naught. It's partial isometry, which is actually unitary between the p range of p1 to range of pn. So this is actually equal to xi naught eta naught. Because this un is actually partial isometry, but between p1h to pnh, it is unitary. So because of that, this will be equal to this. And this is precisely equal to xi naught tensor f, eta naught tensor g. So this u, whatever we have defined, this is small un, sorry. So this unitary we have defined preserves the inner product on a total set, so it extends. Okay. So u extends to unitary between x naught tensor L2n to h. Now you have to verify the property that it takes, this property. U of one tensor B of h is m. That's what you have to verify. Okay. And it's a unitary, it's onto also, because you will get all scalars. Okay. It's onto also. Anything in this Hilbert space H is given by direct sum of vectors. Okay. It will get all the vectors, right? It will get each and every vector. So that's all. The nth Hilbert space, you will get a vector. That's all. The range of these things is total. The range of this total set is total there. Okay. So if it is clear, then I can say. If it is not clear, I will ask you to write it down and convince yourself. Okay. Everything is clear. So U extends to unity. You take how this goes. How it will take the un um star. It will just see what are the operators here. One tensor B of L2n you want to take. You want to prove this. Okay. U of this U star equal to m. Okay. We know m is given by all this. See, there are two things. If x is in m, we have shown that x is given by those scalars and this partial isometry is written like that. And any such things will be in m so that it defines a bounded operator. For example, if you take finitely many of them, this lambda ij, you take finitely many of them, that will be in m because that's just a linear combination of all those partial isometry. And the strong convergence is exactly that. Okay. So it is the limit of all those summation n and m, this summation, I mean, it is just the limit of, see, m is equal to the strong closure of summation lambda nm x that un star finitely many, right? Now, if you take u star m u, you will get precisely, if you take finitely many of them lambda nm, you will get the lambda nm as a matrix here, finitely many of them on this, or you don't have to worry. It is just one of them. So if you take UN of UN UM star, U equal to 1 tensor ENM, where ENM is a matrix with entry 1 at the nth place, 0 everywhere else, which is a matrix on L2N, which is an operator on L2N. So it will be clear that it will take B of L2N to here, M. If it's not clear, you write it down, it will be clear. I leave it as an exercise. An exercise to write it clearly. You take any partial isometry, it will be precisely that. And this is just the strong limit of this. I mean, this add this map, add U of X is equal to UX U star, this map. It takes strong, I mean, it's a very nice map. It takes norm convergence to norm convergence, strong convergence to strong convergence. So if something is strongly closed something, it will take the strongly closure of the ring, right? So because of that, all these things will imply that this is equal to that. You can easily check. Okay. If it's not clear, you ask me. It's stop it.